Welcome to the part third of the model architecture. In this architecture, I have already imported the libraries and some structure of the module which we are going to use. And we have already seen that in our binary classification problem. And the libraries I am going to use torch.nn, torch, PyTorch lightning. And from PyTorch lightning, I am using model checkpoint, learning rate monitor, model checkpoint to save the model checkpoint after each epoch, and learning rate monitor will monitor the learning rate. As we are going to use cosine annealing learning rate monitor, the goal of which is not to use a constant learning rate, but we are going to use a learning rate scheduler. Actually, I have to import lightning module, which I have forgot. From PyTorch lightning, import lightning module, seed everything, and trainer. We have already seen these things in detail. Seed everything is to make reproducible result, and we are also using classification report. So at the end of this training and validation process, I want to see how much accuracy, precision, and recall I got. I am also using torch metric to utilize the accuracy functionality of the torch metric to monitor my model. So let's go with the model architecture. I am going to utilize a model from PyTorch Hub. Let me show you the PyTorch Hub, PyTorch Video Hub basically. Okay, if we go to this PyTorch video, in the PyTorch video we can go to this models. In the model section we have this hub folder, and in the hub folder we have this readme file. And here we can see that there are different models such as Torch Hub, which you can see in Torch Hub name column. And the lightest of all this model is the efficient X3D XS, and we are going to utilize this. Let me import this model so we can see it. So I am creating a variable video model equal to torch.hub.log, and here we are going to pass the path of the model, which is Facebook research, PyTorch video, and the name of the model. Name of the model can be copied from here, and the pre-training can be set to true. Okay, let me print this model and go to the last layer of this model. The last layer of this model, which is actually linear layer, have input feature 2048 and the output feature as 400. We have two choices. Either we modify these output features to 1, or we can add another layer after this output feature, which have one neuron as the output. Let's go to the second approach, and let me import this model into our model class. Here we go. The next thing, I have to define a ReLU activation function, which will be after the last layer of this model. After the ReLU activation function, I have another linear layer which will take 400 input neurons and will output 1 neuron. Okay, that's fine here. After that, I am going to define my learning rate, which will be 1 raised to power minus 3. This is actually the initial learning rate, and we are going to use a learning rate scheduler. And I am also going to use batch size of, let's say, 8. Maybe we need to reduce that depending upon the size we can have in our GPU. And this is actually a RTX 3070 Ti GPU. And you can also see the tutorial on how to install this GPU if you have one on the Ubuntu machine. And the number of worker will be 6. Actually, this is very important because if we have utilized too many workers to load and manipulate this data, this will slow down the system processing. And if we have reduced the number of workers to like 2 worker, 1 worker or 0 worker, this will also increase the computation time such as data loading and data augmentation. So 6, 4 and 8 is a very good number and it always works for me. There is a guideline by PyTorch Lightning that how you can choose this number, but this is a good number for me. And next we have to define the metric which we are going to use for the evaluation purpose. It is accuracy. You can use F1 score if your data is imbalanced, but for me the data is balanced, so I am going to use accuracy. And the loss function will be binary cross entropy with logit slots. Okay, next thing I have to go into my forward function, and here I can define as self.model, and my tag size will go to this model. From this model I got 400 neurons, which will go to the ReLU activation function, and after the ReLU activation function I have a linear layer equal to self.linear. Okay, this is the forward function. Next I have to define the optimizer, and we have also need to define the scheduler in the optimizer. So I'm going to define a variable OPT, and from torch.optim.atomw, from torch.optim I am going to import atomw optimizer. Actually, atomw optimizer give me better performance than atom optimizer. That's why you have seen me using atomw optimizer everywhere. If you go with this approach, this is totally fine, but this will give you a constant learning rate, and I want to have a learning rate scheduler. So I am going to define scheduler. Hopefully I spelled the scheduler right. Okay, it's correct. And next I am going to utilize the scheduler we have imported earlier, which is cosine annealing learning rate. And this scheduler will take the optimizer which we have defined earlier, T0, which is a parameter, its value can be 10, ETA min, which is what is the minimum learning rate you want to have. We want to have 1:6 minimum learning rate. Last epoch equal to -1. Okay. Now I have to return the scheduler and the optimizer both combined. So I can do it as optimizer, and then optimizer. Actually I'm going to return a dictionary, a scheduler and the learning rate scheduler here. This is the optimizer. Next I have to define my training data loader, training step and training epoch end.